Okay, so let's get right into it. We usually think of numbers as things we can, count or measure along a line. But what if there's a whole hidden world of numbers out there? A whole new dimension that's not just beautiful, but also incredibly powerful for describing the world around us. Well, today we're diving into the absolutely elegant universe of complex and imaginary numbers. Our whole journey kicks off with a problem that looks super simple. Check out this equation. X squared plus 1 equals 0. Now, if you try to solve for x, you're going to get x squared equals -1. And right there, we hit a wall. I mean, what number, when you multiply by itself, gives you a -1? A positive times a positive is positive, and a negative times a negative is also positive. So with the numbers we all know and use, the real numbers, there's just no solution. For a long, long time, this was just a dead end in math.
So what did mathematicians do? They did something kind of genius. They invented a new number. It was a bold, brilliant move. They called it I for the imaginary unit, and they just defined it to be the solution. They said, let I equal the square root of -1. And the most important part of that definition is this. I squared is -1. And with that one single invention, the impossible problem was suddenly solved.
Now, I know what you might be thinking. Just making up a number? It sounds a little weird, right? But honestly, it's how math has always moved forward. Think about it. We invented negative numbers to solve equations like x plus 5 equals 0. We came up with fractions, or rational numbers, to solve stuff like 2x equals 1. The imaginary unit I is really just the next logical step in this long tradition of expanding our toolbox to solve new puzzles.
So with this new number I in our back pocket, there's a big question. Where do we put it? It clearly doesn't fit on the good old number line we're used to. And this right here is where things get really, really cool. We're about to go from a simple line into a whole new dimension.
Right. Just picture the regular number line. You've got all the real numbers, positive, negative, fractions, decimals, you name it. They all live together on this single one-dimensional line. You can go left or you can go right. That's all you got. But our new number, I, it needs its own space to exist. And the solution, which you can see right here in this Argand diagram, is just beautiful. We take our familiar horizontal line of real numbers, and we just add a vertical axis for our imaginary numbers. And just like that, our one-dimensional line literally blossoms into a two-dimensional plane. Welcome to the complex plane. Any number that lives on this plane is what we call a complex number, and it has a standard form z equals x plus iy. It's really just like a set of coordinates. The x is the real part, it tells you how far to go left or right, and the y is the imaginary part, it tells you how far to go up or down. Suddenly, every single point on this entire flat surface is a number. Okay, so we've got this awesome new two-dimensional world of numbers. But how do we actually do math here? How do you add and multiply in this new space? Let's take a look.
So the good news is addition is incredibly easy. If you've ever dealt with vectors in physics or math class, it's the exact same idea. You just add the real parts together, and then you add the imaginary parts together. It's as simple as that. And this slide gives us a perfect picture of what's happening. See that first arrow? That's our first number, 4 plus I. Then we add the second number, 2 plus 3i, by just sticking its arrow onto the tip of the first one. Where we end up is the answer, 6 plus 4i. And you can see how they make this nice little parallelogram, super intuitive. Multiplication, on the other hand, well, it looks like a total mess, doesn't it? You can do the algebra, multiply it all out, remembering that I squared is -1, and you get this big formula. I mean, it works, but it's really clunky. What does it even mean? Geometrically, what are we doing? It's not obvious at all. There has to be a better way to think about this. And guess what? There is. The real secret to understanding complex multiplication is to completely change our perspective. Instead of thinking about x and y coordinates, we need to start thinking in terms of distance and angle. This is where the power of polar form comes in. So, it turns out every complex number can be described in two different ways. The first is that rectangular form we saw, x plus iy. That's kind of like giving someone walking directions. Go 3 blocks east and 4 blocks north. The polar form, though, is more like just pointing. It's over there, and it's that far away. This image shows it perfectly. Instead of using x and y, we can define any point z by its distance from the center, which we call r, and the angle it makes with the positive real axis, which we call theta.
So that distance, r, has a fancy name, the modulus, but really all it is the size of the number, the length of that arrow. And we can find it super easily using the Pythagorean theorem, because the real and imaginary parts make a nice little right-angled triangle.
And that angle, theta, is called the argument. It just tells us which direction the number is pointing. So together, the modulus and the argument give us everything we need to know, and as we're about to see, it's a much more powerful way to see things.
And here it is. This is the big aha moment. This is why polar form is such a game changer. That messy, horrible algebraic formula for multiplication turns into this ridiculously simple geometric rule. To multiply two complex numbers, you just multiply their lengths and you add their angles. That's it.
So what this means is that multiplication in the complex plane isn't just some abstract algebra anymore. It's a physical action you can actually visualize. It is a rotation, and it is a scaling. Multiplying by a complex number literally rotates and stretches every single point on the plane. And that is a truly profound insight. So what's the magic glue that holds all of this together?
Well, it's this absolutely stunning equation, Euler's formula. It shows us that raising the number e to an imaginary power is deeply fundamentally connected to rotation. It's the bridge that connects the exponential function to trigonometry, all through the number I. This is the engine that makes that beautiful multiplication rule work so perfectly.
And now, using Euler's formula, we can arrive at what many people believe is the single most beautiful equation in all of mathematics. It ties everything we've just talked about together in a way that is, well, it's just breathtaking.
This is Euler's identity. Just take a second and look at it. E to the power of I times pi plus 1 equals 0. It looks so impossibly simple. And yet, packed inside this tiny equation are the 5 most important numbers in all of math.
And this is why it's so incredible. You've got 0 and 1, the absolute foundations of all arithmetic. You have pi, the star of geometry and circles. You've got e, the bedrock of calculus and growth. And then you have I, the cornerstone of this entire imaginary world we just explored. 5 superstore constants from completely different areas of math, all linked together in one perfect, simple statement. It's like finding a grand unified theory on a Post-it note. So think about where we started, with a simple little equation that had no answer, and we ended up here at an identity that reveals this deep, hidden unity in the mathematical universe. It just leaves you wondering, if this beautiful, shocking connection exists, what other profound secrets are just waiting out there for us to find in this elegant, two-dimensional world of numbers?